one thing you should be thinking about when you think about the MCTH method is like, it's more like a contraction method. That is, you have a problem and you try to reduce it into a smaller space. If you want to have a picture of the dynamics, you can imagine the wave packet as something that evolves in the Hilbert space. Instead of defining the basis that spans the whole Hilbert space, you can define a basis that tends to follow the wave packet as it evolves with time. That's why we can use a small number of functions and still describe quite accurately the dynamics of the system. Obviously, if the wave packet starts to spread out, it's become a little more difficult to do it. But if the wave packet is still very much localized, it's very efficient to solve the dynamics. But this type of contraction, you can imagine that you can apply it at several layers. So in the first layer, you can perform one level of contraction and then perform several other layers of contraction, and your wave packet can become extremely compact. And it turns out that by applying this kind of successive contraction, you can even go from an exponential scaling to almost a polynomial scaling in the cost of your calculation. So what is quite interesting is that this family of method has been around for some time in various fields. In condensed matter, there's been this DMRG method, which is actually some kind of special case of the multi-layer MCTGH method. So it's more like an approximation, but most of all, it's more like a tree description of the problem where at each level you kind of apply some kind of contraction. So in the case of DMRG, it's called matrix product tensor train, but if you reform this graph correctly, you are actually able to obtain something that looks exactly like this. So there's kind of a generalization that is provided for this type of method, and they have been very efficient. And like I said, you can go really, if you apply several layers of contraction from an exponential scaling to some kind of polynomial scaling, and that helps to describe the dynamics in a much better way. Additionally, what I can say about the MCTGH method is that it's computationally cheaper than the brute force method that I mentioned initially, but it's still much more expensive than those other quantum dynamics method like ring polymer molecular dynamics and train molecular dynamics, because they rely on classical trajectories. But most of the time, when it's possible to run this kind of calculation, they are considered as the benchmark because they are exact, as a matter of fact, if you can run them. What is really beneficial is the fact that because you have the wave function, you can really follow the system, study the system, and get additional information from the propagation. And to close a parenthesis about this MCTGH method, I want to mention that there are many flavors of this method. There's the method that we are trying to use for this code, which is this one. They almost all originate from Heidelberg in Germany. And a few years after this one was developed, they developed this second one for the boson, so more towards condensed matter and ultra-cold system. At Berkeley, there was someone who was involved in developing the MCTGH method for fermions, which was also quite efficient, but I think they don't maintain the code very actively. And more recently, they developed another method for identical molecules, so both for boson and for fermion. So that's about the method we are using. And I'm going to come back about some of the limitations, some of the difficulties of using this method. But first, I want to return back to the problem that we had to deal with. So when we want to study that system, the first step we want to do is be able to prepare the system in the ground states. That is the state of the system before it receives the radiation. And for this kind of calculation, we actually do a relaxation. And the relaxation is propagation in imaginary time. And then we can get to the ground state of the system. So the system coalesces into the ground state. And from that, the propagation, we have the actual state of the system, and we can then apply the radiation, electric field, or light, and then follow the propagation of the system and extract the wave packet. So these are more or less the set of coordinates I use for this specific calculation. And if you just want to think about the size of the Hilbert space in terms of point for this specific primitive basis that I've defined here, you'll realize that you'll need about something of the order of 10 to the 15 points. Thanks to the usage of MCTGH, I just have to propagate about a median function and get the result of a very good accuracy. So it's a heavy fraction in the cost of the calculation. So once we have our initial state, what do? We apply the dipole moment surface on that specific system, and then we can propagate the wave packet for a specific amount of time. In this case, I did a propagation for about 10 picoseconds, which is quite long, to be able to resolve all those features. After that, while the system is propagating, you can record the autocorrelation function, and the infrared spectrum that we are interested in is obtained by a Fourier transform of this autocorrelation function. So here you can see some of the result of the propagation when we start from the ground state of the system. And you can compare it with some experiments that were done in 2010. And you can see, for instance, the set of features that appear in both spectra. The feature at 3600 is the same that you can see here. There is one specific feature at 3640 around here, which is the FD that is displayed here. And there is also a set of structure that you can see here. This specific feature N is not actually due to the water dimer. When the system absorbs a lot more water, because this experiment was not too clean, you see that this feature increased. So it's mainly due to other water cluster. But you can also see this specific feature SA, which is actually problematic and was not observed in the initial spectrum recorded from China. But we also have something in this energy range that we can clearly identify. So as I told you before, the fact that we are able to have the wave function give us an additional asset. What we can actually do, because we are able to deal with the wave function, is that we can create artificial excitation of the system. And that's what we did. We put some quantum of vibration in a specific vibrational mode of the system, and we can then perform some cross-correlation study and see specifically in the spectrum where this specific type of vibration is likely to appear. For instance, we can see that the bond OH stretch is likely to appear around 3600. Same with all the other vibrational mode of the water dimer. And this is particularly useful because when we can obtain this specific spectrum, we can say, okay, this specific mode that we have around 3600 is due to the OH stretch of the water donor. Or this other specific feature that we have around 3650 is this blue feature that is due to the symmetric stretch of the acceptor. So we are really able to say, okay, these specific peaks that you see on the spectrum come from this specific vibrational mode. And this is not something you could have been able to do if you were just using a classical dynamic simulation without prior knowledge of the wave function. But actually, we can go a little bit further than that. Like I said, initially, there are two goals that we had. First, be able to identify all the features that you can see in the spectrum, but then be able to explain the splitting, some of the splittings that you can see, for instance, in this part of the spectrum. To be able to understand that, you have to take a step back and realize that, first of all, those experiments that are done in the lab are almost never done at 0K. So there's always some level of temperature. And because of those temperatures, the system is not just, the ground state is populated, but several excited states are also likely to be populated. So here on the left, I plotted some 2D contour plot of the wave function. This is for the ground state, and this is for an excited state, which actually corresponds to the permutation between two hydrogen water in the acceptor. They are separated by about 12 wave number. And here I obtained, this is a spectrum obtained by the propagation of this state, which is actually the real ground state of the system. And this is actually a ground excited state of the system. And you can see that those two spectra have some features that are similar, but some difference with respect to the assignment of the peak. And it turns out actually that when you combine those two spectra, you obtain something where you, if you are a little bit careful, you can realize that there are now about 3 peaks that occurs in the spectrum. And that corresponds more or less to what we are able to see in the experiment. So more or less, we have the understanding that some of the features that we obtain are not only due to the ground state, but they are also due to the excited state. And if we use some spin statistics and other parameters, we can very properly determine those specific features. Also, I say this work is not completed yet, so some of this propagation needs to go for a longer time so that you should be able to very well identify some of these peaks that you can see here. So more or less, our task, our duty is we clearly understand what is going on in this system, and it turns out that it matches some theoretical predictions that were done almost 40 years ago for this specific water dimer, but they had no numerical validation for this specific calculation. But now I'm going to go a little bit further, not about this problem, but what we want to do later on. So what occurs is the fact that when we want to solve the problem, like this idea of molecular quantum dynamics using the wave function, because of the way you do the calculation and the fact that you have to deal with a multidimensional integral, it turns out that it's beneficial to have your Hamiltonian expressed in what is known as the sum of product form. And that sum of product form is just a sum of one-dimensional term or low-dimensional term, which is expressed as relation 17. When you have to deal with a system, then you have a kinetic energy operator, the potential energy operator, and maybe an external field that could be added to the system. So most of the time, the kinetic energy operator is in the right coordinate frame. If you use Cartesian coordinate, it's good enough. If you use Cartesian coordinate, it's good enough. But most of the time, we rely to what is known as polyspherical coordinate, which is a specific way of doing the transformation of the coordinates into some that are more appropriate for the dynamics. Luckily, there is some code that is around that allows you to transform any set of coordinates to the appropriate coordinate system. So most of the time, the kinetic energy operator problem is fine and resolved. What is actually an issue is the potential energy surface. And this is actually most of the time the bottleneck to perform this type of simulation. Quite often, the kind of potential energy surface that one can have could just be a Fortran program that can generate you an energy for any set of configuration that you may have. But because we do the dynamic in a very specific set of coordinates that are appropriate, for instance, to describe a dissociation or a reaction, we really need to have our potential energy surface in that set of coordinates. So most of the time, it's not easy to do. But for this work, we were lucky that there was a method that allowed us to do something of this kind. It's called Monte Carlo CPD, canonical polyadic decomposition, which is a very smart technique, and I may eventually talk to you about that. But what I'm trying to show here is, for instance, the initial potential cut of the potential energy surface and how we are able to represent it using that method. So we have a very good root mean square error, and we still have our potential energy surface expressed in the sum of product form. So to conclude, I wish I was able to convince you that we have a very efficient and accurate method to treat and study, understand what is going on in the water dimer, provide some explanation to a debate that exists for several decades. Our goal is to be able to study water cluster of bigger size, bigger and bigger sizes. And this type of method seems to be the best method to try to approach those problems and at least understand the features that are observed in the spectrum. Now, one of the main limitations that we are experiencing is actually due to the potential energy surface. And one way to go would probably be the possibility of having machine learning potential energy surface expressing that sum of product form directly. And that would probably be very useful to be able to treat this system. The fact is that because of the lack of good quality potential energy surface in the range of interest, there are many studies that have not been tested and tried, and we don't know exactly what we are able to do for this specific type of system. So I would like to thank you for your attention and hope to see you in Rwanda in the near future. So thank you.
Thank you. Thank you so much for the beautiful talk. We're a bit short in time, but I can do a Q&A question.
Hi, thank you. It was a great talk. And can I understand when you presented the presence of excited states to also the presence of some complicated conical intersection? Are you just referring to vibrational excited states, but you're still having your ground state for the electrons, or?
Yeah. Yes, the method is sufficiently flexible that you can also deal with excited states. But this study is just done on the ground state, like the infrared spectrum just characterizes the ground state, but the method has enough flexibility to be able to add several excited electronic states in the description. And it's done quite frequently, yeah.
And so I guess that my next question is it is it known whether in the potential energy of, well, the dimer potential energy surface, both the ground and excited state, is there any known conical intersection that could be relevant for this?
There probably is, but that's not what we are actually studying, because, well, if we were to study an effect that has to involve UV radiation, yes, probably we are going to see several excited states involved in the process, but we are really very low in energy in this specific case. So I don't think we access that range yet.
Okay.
Yeah.
Thank you.
Yeah.
Thank you. Thank you. And
Is there any question? Oh, no.
our next speaker is going to be Sinead Griffin from the Lawrence Berkeley Laboratory, and she's going to tell us about new phases of matter from first principle calculations.
Griffin. So, yeah, that's fine. This one, I guess. All good. Hi, everyone. Morning. So thanks to the organizers for giving me a chance to talk about this. I kind of revised my title because I gave a really vague one because I hadn't decided if I was going to talk about dark matter or not. So I gave a title that covered all things I could possibly talk about. But I decided to talk about non-equilibrium topological materials today. Okay, so why do we care? So, you know, you probably saw even recently, there's a lot of these papers about, you know, most materials are topological, right? There's all of these nice symmetry indicators to check if materials are topological or not. But that relies on crystalline materials, right? So a lot of these markers for topology in real material systems depend on crystalline symmetries and at equilibrium, and they really do depend on band theory, right? I think someone mentioned yesterday, you know, whoever thought like we'd still be doing band calculations of different materials and discovering new things. But it really relies on having translational symmetry and crystalline symmetries. So I'm going to say, well, let's just forget about that. Let's pretend we don't have crystalline symmetries anymore at equilibrium and see what happens. This is just kind of to reiterate this, and maybe for people who don't work in topological materials. Topological phases are really often classified through symmetry. There's lots of different ways of classifying these things. I'm giving you a very brief summary. You can kind of classify them into things called topological band insulators or topological crystalline insulators. But on the right-hand side, I have a cartoon picture of what happens in these materials. So this trivial insulator is what we're used to, right? This is a boring semiconductor. So we've got a finite gap between a valence and conduction band, and each band has the same sort of orbital character. Okay, so then we do something to our material, right? We squeeze it, or we do something to the Hamiltonian that causes a band closing. And then we sprinkle in some spin orbit coupling, and what happens is that you get this band inversion. Now, this is actually a really nice way of thinking about where this topology comes from, or where these knots come from. Because if you follow the red, what I have here, if you follow the red, you can see that you can't continuously connect the red parts together, right? So it's like we have a knot in our band structure that we can't get rid of. And this is actually how we check for topology in these types of crystalline systems, is we actually pull the band structure as far apart as we can to try and get it to go to the atomic limit. And if we still have those knots in the band structure, then it's got some sort of topological characteristics. So this is what a topological insulator is. Okay, so then we take our topological insulator and we put it inside a crystal structure. And what that crystal structure does is it'll actually add some symmetry protected crossings, right? So you'll have some other symmetries that are added on top of your topological insulator that can cause you to have these sorts of symmetry protected nodes, so pinch points in your band structure. Okay, but all of this relies on having these sorts of crystalline symmetries. And there's been a lot of work on this already. So We have these catalogs of topological materials, all of these searches. We got a bit into this last year. We did a high throughput search for magnetic topological phases in my favorite class of materials, which are transition metal oxides. And we were able to find a bunch of new magnetic topological materials that way. Okay, but we're going to forget about that today. We are going to think about, well, what happens when we either get rid of translational symmetry, so we don't have crystalline symmetries anymore, or if we start thinking about dynamically controlling these sorts of phases. So, shaking up the material, pump probe experiments, and can we think of ways of actually controlling this in a systematic way? Okay, so the first thing I'm going to talk about is dynamical control of this topology. And the kind of motivating drive for all of this is, can we do the same tricks as we do with oxides, right? Multiferroic oxides, strain and stabilizing different types of phononic modes. Can we use those same tricks to actually design topology in these types of systems? And then the second thing I'll talk about is what happens if we throw out translational symmetry, and how do we think about topology in those sorts of cases? Okay, so this is what we want to do. So how do we control topological order in a crystalline material? Well, I've already told you that symmetry is really important. So we can do it by controlling symmetry. In the same way in ferroelectrics or magnetic materials, we can think about controlling symmetry breaking. So there's kind of a counterintuitive thing, though, that happens in topological phases. So in a ferroic material, we require symmetry breaking, right? So if we want to have a ferroelectric material, we need a break inversion symmetry. If we want magnetism, we break time reversal symmetry. But topological phases, actually, you want symmetry, right? You want higher symmetry to get that symmetry protection. So this is kind of the concept that we have. On the x-axis, I have a control parameter. On the left-hand side, I have some sort of topological order, right? We've got some Weil or Dirac semi-metal. And this will be in high symmetry phase. And on the right-hand side, I have the ferroic order where you've broken the symmetry and you've got some sort of ferroic order. And the idea is that we want to break the symmetry to control in between these two different phases. Okay, so I'll give you an example. If we want to control a topological phase by, for example, applying an electric field, we'd want to have a polar material. So we want to have polarization that requires you to have inversion symmetry breaking. So then we look for topological phases that are preserved by inversion. So then you have a natural symmetry route of switching between these things. This is a big long chart of the different types of crystalline topological phases you have, where you have the different types of orders. And as I said, there's long catalogs. All I want you to take away from this is that we have lots of options to do this. So we have lots of options to look for this sort of ferroic control of these sorts of topological phases. Okay, so the system we're going to look at is we're going to look at these things in something called higher order topological insulators. And like I said, this is really guided by symmetry. And to try and find something that has a very rich phase diagram, we want to go to something that has very, very high symmetry. And we have these ways of like categorizing all of these types of things, but the essential part is that we get this bulk boundary correspondence. So on the left-hand side here, I have like a canonical topological band insulator. In this sort of system, the bulk is insulating and you get these surface states. In these special types of higher order ones, basically, because you've got this very high symmetry, the edge modes also have different symmetry constraints on them as well. So these are the types of systems that I'm going to look at. And the reason for this is because we want to look for them in oxides. And, as I said, my favorite materials are oxides. That's part of the reason. But also people like Darrell Schlamm can grow these really well. So you can do MBE growth of these sorts of systems, and we can strain tune them to a really high level. But you probably know that there's not that many topological oxides, and it's a really simple reason for this. It's just chemistry. So in order for you to have this sort of band inversion, right, we need to have this gap closing or very strong spin-orbit coupling to be able to knot these bands around each other. But in perovskite oxides, your d orbitals and your p orbitals tend to have these band gaps there that are over an AV, right? That's why they're good dielectrics. So it seems that we're kind of stuck. If you want to look for oxides, we need to get rid of this DP driven band gap. But what we can do is instead invert the crystal structure. So rather than looking for perovskites, we can actually think about inverting the crystal structure to try and invert that DP hybridization. And that's where we get anti-perovskites. So we're going to look for these sorts of topological phases in these anti-perovskite systems. And this actually works, by the way. So it might seem trivial that you just invert the structure and get the band gap inversion, but it does work. And so I'm not the first person to think of this. Jen Cano had a paper about 2 years ago where she actually classified topology in these anti-perovskite systems, and Sasha Belatsky as well the year before had identified a lot of these chemistries already. But what I want to do is actually figure out how we can control them. And so if you look in the ICSD and see if they've actually made these materials, they have, but all the papers are in German. So making these anti-perovskite systems it was really popular in Germany about 10, 20 years ago. So they have been made, but if you look, a lot of them actually don't have this really fancy cubic structure where you get these interesting topological phases. So here I have the calculated band structure of this cubic anti-perovskite, and this is this chemistry, the strontium silicate one. So on this x-axis, I have the high symmetry points. My Fermi level is the dashed line. If you zoom in here, you see that we get these topological band crossings in the cubic one. But if we go to the PNMA phase, which is the ground state of this system, it's gapped, right? Trivial and gapped and boring. So do we have actually a way of then figuring out how we get from one to the other, and can we stabilize the cubic phase? Okay, right. So on the left again, I have kind of the summary of this topological, high order topological phase, and on the right is the orthorhombic. Now, in getting from this cubic high symmetry phase to this orthorhombic phase, there's actually 4 different phonon modes that are involved in this. And each one has a different influence on symmetry. And so I'm just going to point out one example here, this X5 minus mode, which is basically you get these silicon atoms moving towards the center here, and then they're anti-phase in this direction, the Z direction. So actually, when you include this phonon into the structure, just this X5 minus phonon, this actually breaks the mirror plane and changes this from being this higher order topological insulator into being a weak topological insulator. So this is the general strategy of selectively including different phonon modes and turning on and off different symmetry elements, and that allows you to turn on and off different types of topological phases. So here's the kind of overall picture. Depending on which symmetry mode you have, or a symmetry adapted phonon mode you have a different way of turning on and off different topological elements. So I'm going to just give you this summary to tell you that basically we can selectively tune different types of phonon modes to get kind of a topology by design in these sorts of systems, in the same way that we do with multiferroic materials, the same sort of design principles. We can play the tricks with axial strain as well that we do, right? So we can go from this what's called a Z8 topological insulator to being a Z4 one if we use uniaxial strain. Okay, so this is all, using what we're used to, right? Strain and phonon engineering. But can we do this dynamically, even if these phonon modes aren't stable? And this is the idea of using pump probe experiments in the terahertz regime to selectively probe these types of phonon modes. So rather than using temperature, using strain to tune in between these 2 different phases, can we do it dynamically? And these tricks have been done a lot with Andrea Cavalieri, for example, in the Max Planck Institute, where he's turned on and off different types of superconducting orders, charge density waves. So it's the same sort of principle. Okay, and just to give you a really brief overview of how these work, you can use terahertz pulses to probe these IR phonons, right? They're in the right energy range for terahertz probes. And if we do this at low fluence, we get this sort of IR active phonon mode, but it's harmonic, right? So this doesn't really do much, right? You'll get a flickering of your mode, but it'll be harmonic. However, if we turn up the flux, right, when we want to pump these phonon modes, what will start happening is we'll start getting the higher order terms. We'll start getting the nonlinear phononics. And specifically, you get this trilinear coupling, this IR squared QR coupling, which can actually cause you to have this phonon rectification through this trilinear coupling. So on the right-hand side here, I have this calculated for one of these anti-perovskites. On the x-axis, I have the Raman active mode. On the y-axis is the energy, and you can see you get this rectification through this trilinear coupling. But this is really interesting because this means you can dynamically induce structural changes in your system. So you can dynamically induce a symmetry adapted phonon through this sort of mechanism, and use a pump probe experiment to actually look at it. So when we do this for these anti-perovskites, this trilinear coupling, and as you can imagine, you've got loads of phonons, so there's quite a a broad search space there, the phase diagram of what modes couple. In this system, it's actually a T1 mode that couples the strongest to this Raman active one. And when we actually do the calculation, you can see here, we actually open up this band gap and cause it to become trivial. So doing this dynamically can actually allow you to turn on and off topology in these systems as well. Okay, how's my time? I don't have a watch here. Yes, great. Okay, I'll tell you about amorphous stuff. Great. Okay, so that was the first part. So we can do this dynamically. The second one was we're going to throw out translational symmetry and see what happens. So like I mentioned already, a lot of these ways of classifying topology really rely on crystalline symmetries. So we have these symmetry protected band crossings. All of what I told you previously was all reliant on these sorts of symmetry indicators. Now, one of the motivations I always say is that real materials are messy, and of course we have disorder in there, but there's actually far more amorphous materials in the world than there are crystalline ones. It's much easier to make an amorphous material than it is to make a crystalline material. So actually finding and trying to understand topology in amorphous materials is also useful if we do want to make, for example, a topological quantum computer. Okay, so the question then is, can we think about, like, how do we even start thinking about topology in amorphous materials? And so I'm going to tell you two quick stories. The first is just looking at disorder. So can we induce a non-trivial topological phase in a trivial one by using atomic disorder? So that's our kind of first step towards understanding what amorphous is. And then I will actually go on to tell you what happens if we take a known topological material, bismuth selenide, and make it amorphous and see what happens. Okay, so this is the first story I'll tell you briefly. And we started off with this bismuth tellurium iodide compound, and this is actually a pretty nice story. So Paul is an experimentalist, or he was formerly an experimentalist, and when the labs closed down 2 years ago, he was really bored because he couldn't get in, so he asked me if he could be a theorist for a while. So I got him on loan from Francis Hellman's group, and he actually did all of this work. So his first PhD paper was actually a theory paper, even though he's been in the lab for 4 or 5 years. So this is all his work. So basically, we took this bismuth tellurium iodide. Here on the right-hand side, I have the crystal structure. So you can see here, it's a Rashba material. So you get this spin-dependent splitting in this material because it's inversion symmetry broken. But what we wanted to do is actually see if we had a way of closing this band gap. And there was work already that looked at pressure to induce a band gap closing in this material. So we weren't just shooting out of the blue, right? We knew that this material was close to a topological phase transition already. So what Paul did was he introduced random atomic disorder into the system. You can see kind of, that's what's indicated by these spheres. And in small enough amounts that it would be possible to make this an amorphous material. So he looked at the typical bond distributions that you get in an amorphous phase and actually used that as the magnitude of the bond distortions that he did in this material. And well, I wouldn't be telling you if it didn't work, right? But it works. So you can see that as you increase the amount of atomic disorder you can get in the system, you get this band gap closing and then the band inversion, and it's a topological insulator. And this is really easily described by looking at the crystal field splitting in the system. Essentially, you get this bismuth p orbitals and the tellurium p orbitals, and as you just increase the pz orbital overlap, you get the band inversion. So it's a very simple route to actually causing the band inversion in this case through modifying that pz overlap. Okay, so that was the first case. So we're able to, make a material topological. But what if we start off with something that's topological and actually make it amorphous? And that's what we did with bismuth selenide. Okay, so we're not the first people to think about amorphous topological materials. There's theoretical work that has formally categorized a topological indicator for systems that lack translational symmetry, and that's called the Bott index. So like I kind of described to you, the way we classify topology is by linking them to this atomic limit and seeing if we have knots in our band structure. The Bott index does a very similar process, except you're actually comparing unitary matrices and seeing if they're commuting or not. So it's a very similar concept in how we basically make comparison to something that's topological or something trivial. We see if we can deform one into the other. And so this Bott index is actually a global property of a system. It doesn't rely on symmetry. So it's very applicable in these sorts of systems, especially when we've got disorder or amorphous. However, this is a theoretical description. It doesn't tell us anything about real materials, right? We want to actually describe real materials. So there's a few different ways that we've looked at this. We've looked at effective models through a patch formalism. So basically a type binding Hamiltonian where we, rather than using a regular lattice, we use different types of ways of describing amorphous networks. Here's an example on the right here. This is a paper by Agarwala and Shenoy from 2017, where you can see the edge states. But what I'm going to talk about a little bit today is what is a good quantum number in an amorphous material, and then how do we actually calculate it. And I actually was reminded of this yesterday, that the person in my group who did these effective models for the patch formalism was an undergraduate, Amy, who got to meet Richard when she was an undergraduate in Berkeley. And as she'd been reading Richard's book for the summer. She was working with me for about a year. And, getting to meet Richard was kind of, well, it was a really big deal for an undergraduate because she'd the book and she was like, can I ask him to sign it? And I was like, I'm sure you can. So she got to meet him, and she was the one who was responsible for doing this patch formalism. She's a grad student at the University of Oxford now. Quantum information science stole her. We weren't able to keep her in solid state physics. Okay, so this is how we go ahead and calculate this. So the first thing is to generate good structures, right? We need to actually accurately describe the amorphous network that we have, and I'm going to go into a little bit of detail on that. Then we take these amorphous snapshots. We get our Wannier Hamiltonian, okay, right? Each side in this amorphous snapshot is unique. That's a lot of Wannier orbitals to try and deal with. So the way we actually deal with that big, oh, something's happening on my, okay. The way we deal with that is actually using kernel polynomial methods, which is a sampling technique for these huge matrices that we've generated. And then we can do things like calculate spectral functions. Okay, but first thing, we need good structures. And we use ab initio molecular dynamics to generate these structures. Now, I have this here as the same methodology we use for looking at superconducting niobium oxides. And the reason I have this is because we don't have experiments on the bismuth selenide, but we have experiments on this. So we do quench dynamics, right? So kind of in a way, the similar way that they make these materials, you heat it up and then you quench cool and do relaxations, and then check that what your radial distribution function is and see until it's converged. And all I want to tell you about this is that we do this, we then do a bunch of snapshots and we average them. And we have a way of comparing this directly to experiment. So once we throw out, right, translational symmetry and band symmetry, we have a problem with theory, but experimentalists also have a problem, right? Because we can't use conventional microscopies and spectroscopies if we don't have translational symmetry. But there are some methods for actually measuring structure in these sorts of amorphous systems. And one of the ones is fluctuation electron microscopy, which can give you information about the medium range order in these systems. One of the things that they can measure is the radial distribution function, right? So what's the average bonding environments in these systems? And that's something then we can also measure in experiment, right? We can calculate and compare them. And here we actually we were within 5% of the calculated radial distribution function that was measured in experiment. We also looked then, okay, you can say, okay, you got the structure right, but is the electronic structure right? We did the same, or we use these structures as well to calculate the XAS spectra as well, and compare these with experiments, and they're also a pretty good match to the local electronic structure as well. So this tends to give us very reliable structural information that is consistent with what you measure in experiment. Okay, so now we have a problem. So we've thrown out translational symmetry, and I've spent like the last 20 minutes pointing at band structures and telling you this is how we look for topology. But if we don't have translational symmetry, then our K quantum numbers aren't good quantum numbers anymore. So what is a good quantum number then when we have an amorphous material? And actually, we should listen to experimentalists, right? They kind of told us what the good quantum number should be, because that's how they measure amorphous materials. And the way you characterize an amorphous phase, as I said, is this radial distribution function. So you've got something to do with the local bonding environment that is telling you how this phase is actually characterized. So while the Kx, Ky, Kz isn't a good quantum number, actually its modulus is the spherical symmetry, the local bonding environment, the spherical symmetry of that is actually a good quantum number, and that's exactly what we define. So when we do this, here is our calculated band structure. So here, instead of our K direction, we've got this spherical quantum number, and on the y-axis is our energy. And so in this left-hand side case, we see we've got this Rashba split trivial case, and on the right-hand side, we've got our symmetry protected band crossings. Okay, I think I'm nearly out of time, so I'll really briefly go. Okay, so here's the results. So here's the big wow. On the top, we have, as I said, this calculated symmetry protected band crossing, and on the bottom is the ARPES measurement. So this is measured band structure from Alessandro Lanzaro's group, and you can see we got this this circular thing. You can imagine taking a cross section at a finite energy here, you get this sort of circular feature, which is the Dirac cone. Now, this is a very involved procedure, right? I told you we've got all of these amorphous, we have to do with this AIMD, and then we do anorization, and then we do KPO. You can't do that for a lot of materials, right? That's going to be a case-by-case basis. So we wanted to try and think, well, do we have a way of actually predicting the amorphous TIs without having to go through this long involved process? And, not to day 3 and everything David Vanderbilt has already thought of, but he had already thought of this, not applied to amorphous materials, but to crystalline materials. So he proposed this spin orbit spillage as a metric for identifying new topological phases. And this spin orbit spillage metric isn't actually K-dependent. So you can use it for amorphous materials. So this is what we're proposing actually as a way of identifying new amorphous materials based on something that doesn't involve a very convoluted thing. And that's what we're working on right now. Okay, I'm going to finish there. And I'm going to tell you as well that we also looked at quasi-crystals, but I didn't really have time to tell you about that. This is my group. Paul, as I said, is our adopted experimentalist. He's been doing this, and Temujin has been doing this work as well. And then I'm going to finish off with my collaborators. Thanks.
Thank you, Sinead. Really fantastic talk. We have time for questions. So maybe I can start. In the antiperovskite that you showed, when you were, so in the topological phase, it looked to me that it was a metal. Is it a metal? So is it that so are the edge states at all, localized on the edge?
You're absolutely right. So let me point out to everyone else what's going on there. Okay, right, this is, I think, the clear one, right? So you can see that this part, is this? Yeah, okay, this works. So this is the band crossing here. Now, if I zoomed in really far, you'd see it slightly gapped, but this is not an insulator, right? Even if you squint at it really hard. But with different choices of the A-side cation, so this is the strontium case, with different choices of the A-side cation, you can actually open that up a little bit. So you can basically chemical engineer this to be at the Fermi level and to be really insulating. The other thing as well, which I didn't talk about today, is that you can also start tuning the magnitude of the gap by going down the periodic table to increase the spin orbit coupling as well. So you actually have quite a large chemical space to play with in this system to get that right at the right place.
So this crossing is not protected. This it's gapped by spin orbit coupling.
Yeah.
Any other questions?
Maybe it's a silly question, but why do you have a band gap opening for the orthorhombic structure?
You have the band gap opening because the mirror crossing and there's a C3 symmetry that protects this crossing. They're broken when you have the orthorhombic phase. So basically, the symmetry protected crossings open up.
Thanks.
Okay, if there's no more questions, let's stay seeing it again, and let's move. There are questions in Zoom. Okay, so 1 second. let's answer the questions first.
I have a question. Should I read it out or how to do it? Okay, it's from David. About the last part, the usual understanding of topology in bismuth selenide involves 2D layering, band inversion, even odd parity layer states. How do you understand it in an isotropic 3D amorphous context? Right, exactly. So we're losing all of those symmetry elements, but we still get the band inversion at gamma because we don't have KX, KY, KZ anymore. But it's caused by the band inversion that you get from the PP hybridization in the selenium. So you get the band inversion even though you don't use the same classification that you do in 2D layering.
Thank you. Okay, so our next speaker is Enbeng Dai from UPenn, and he's going to tell us about first principles calculations of ballistic currents.
Good morning, everyone. My name is Jim Banda. I'm working at the Professor Andrew Rapp's group from University of Pennsylvania. But before my talk, I want to thank the organizers, all the organizers for preparing this very wonderful workshop, which I have learned a lot from. So today I will be sharing the progress that we have made in the past 2 years in the area of the bulk photovoltaic effect, and especially how we enable the first principles calculations of the ballistic current. So first, I will talk about the motivation of this whole study, like what the bulk photovoltaic effect is and what the ballistic current is and why they are interested, and why they are so interesting, so that we want to study them. And then we'll go over the general theoretical framework to study this effect. And then I will talk about 2 specific ballistic current mechanisms. They are phonon ballistic current and exciton ballistic current. And then I will summarize the presentation. Okay, so as we know, we have a ever increasing demand for energy resources ever since the industrialization, but we just have very limited stock for the traditional energy sources, such as the fossil fuels. So we have to find new and sustainable energy sources to continue to power the society. And the solar energy has been proposed as a candidate to kind of solve this problem. But as you can tell from this chart, you can see that the solar energy only constitutes a very small portion of all the energy consumptions in the modern society. So that motivates us to find new ways to further improve the PV technology so that we can further use this solar power to at least mitigate the energy crisis. So I mean, for almost all of the currently available solar cells, the underlying working principle is the so-called traditional photovoltaic effect. Basically, it requires a heterojunction, such as a p-n junction, where in the depletion region, there will be a built-in electric field that can separate the photoexcited carriers so as to give a DC steady state current. And because of this very working principle, it dictates that there will be an upper limit for the power conversion efficiency. And for people who are familiar with this PV technology, it's called the Shockley quasar limit. It basically means that the frequency of light cannot be too low because it cannot be absorbed by the material. And it can also not be too high because if the photon energy is too high, then the photoexcited carriers will be far away from the band edge, so that it has to lose a lot of energy when it stimulates the band edge, where it can be harnessed for generating the electricity. So people want to find new mechanisms to build new types of solar cells that can surpass this limit. And indeed, people have observed that for a homogeneous material, if there's no inversion symmetry, like there's no inversion center in this material, then we can still observe some steady state DC photocurrent and illumination. And we call this effect the bulk photovoltaic effect because it appears in a bulk material, not a material composed of heterojunctions. And because the working principle of this bulk photovoltaic effect is very different from the traditional one, it is in principle can surpass the Shockley quasar limit for the traditional solar cells. And indeed, people have demonstrated that in this Nature Photonics paper, the power conversion efficiency for barium titanate, which is a ferroelectric material, and thus it breaks the inversion symmetry, it can exhibit the power conversion efficiency higher than the Shockley quasar limit. So it's very promising and very interesting phenomena. So people want to understand this phenomena, and there were a lot of theoretical studies about this phenomena in 1970s and 1980s, where a lot of important concepts were introduced, such as the shift current and ballistic current, which I'll get into in a few slides. And a summary of those earlier works can be found in this in these textbooks. However, most of these earlier studies, I should say all of the earlier studies rely on very simple models with a lot of empirical parameters. So it's very hard to really quantify the importance of each mechanism. So that basically motivated our group to publish a paper where we use first principles calculations to compute the bulk photovoltaic effect, and we can make some comparison with experiments. So here I'm showing you the result for barium titanate. The horizontal axis represents the photon energy relative to the band gap, and the vertical axis represents the photocurrent. And the solid line represents the theoretical result, whereas the dashed line represents the experimental photocurrent. You can see that within some error bar, so these shaded areas are error bar when considering some uncertainty in the sample dimension, in these experimental parameters, you can see that we can reach very satisfying agreement between the theory and the experiments. So that really, really make people exciting in this area. And ever since then, you can see an exponential increase of the publications in this area. So in 2012, we published this paper, and you can see there's an exponential increase. Okay, so to better understand this bulk photovoltaic effect, or BPVE, we need to know that there are mainly two major mechanisms that were proposed for it. There are shift current and a ballistic current. So they can all be traced back to this very general expression for charge current. It's basically the trace of the density operator multiplied by the velocity operator with some prefactors. And the shift current comes from the off-diagonal elements of the density operator, which can be seen in this n not equal to m in the summation. And so it's really comes from the coherence instead of occupation. And thus it's it's a pure quantum effect, because it's very hard to find any classical interpretation for the coherence. However, if we try to assign some physical meaning to this shift current, we can do some manipulation to this expression. And in the end, we will have an expression, which I will show you later, but it basically conveys the information that the shift current describes such a process where during the photoexcitation, the average position of the wave packet will experience a real space shift. So that will give you a DC current when you shine light on this material. And it's really an intrinsic phenomenon. It doesn't really rely on any kinetic parameters such as the relaxation time. And the shift will be finished once the excitation is finished. So that's for the shift current. And the other mechanism is called ballistic current. It comes from the diagonal part of the density operator. So it really has some very classical interpretation, because it's basically occupation times the velocity, which is really the expression of current in the Boltzmann transport equation. So in order to have this ballistic current, we will have to have some asymmetry in the momentum distribution. This basically means that the number of electrons moving, let's say, to the right, cannot cancel the number of electrons moving to the right, to the left, so that there will be a net current. And this current will appear after the photoexcitation, even though the asymmetry of the distribution function will appear right at the photoexcitation. So these are the two major mechanisms that were proposed for the bulk photovoltaic effect. And for shift current, if you follow this idea that the shift current comes from the off-diagonal density matrix elements, you can do some perturbation theory to it, and you will end up with this expression that as I promised it before. So there are basically two components in this expression. So one is the so-called transition intensity. So basically it tells you how many electron hole pairs will be generated during the photoexcitation. And the other component is called the so-called shift factor. It has the unit. It has a unit of length. So this quantity tells you that how large the real space shift is during the photo excitation. So even though this expression is a little bit complicated, but it's still very easy to evaluate it from first principles. And the computational cost is not that high because it is only a single summation over k1. So once you use density functional theory to evaluate each, to evaluate this the ingredients in this expression, you can get the shift current, theoretical shift current. And here I'm showing you again the figure that we published in 2012 PRL paper. So here I'm really showing you the shift current mechanism. And you can see the agreement is not so, is very satisfying. And you may think, oh, this might be the end of the story. So once we achieve this agreement, then that's it. It must be shift current who can explain the Bokeh photovoltaic effect. But that's not really the end of the story, because we had a new postdoc in our group who did further study, and he realized that when we were calculating this shift current, we have to know how deep the light can penetrate into the sample. So that basically means that we have to know the absorption coefficient of this material in order to get the current that can be compared to experiments. However, we computed the absorption coefficient at the DFT level, and then you may realize, oh, that's not so good, because we know there will be exciton effect, and this exciton effect can greatly renormalize the absorption coefficient. So that postdoc did some further, basically he replaced the absorption coefficient with the one that computed from the Betz-Torpedo equation with the exciton, basically to consider the exciton correction. And after the exciton correction, you can see that agreement is not that good, especially for this component. The magnitude is almost half of the original one. So this basically means that shift current only cannot really explain the full picture of the Bokeh photovoltaic effect, and other mechanisms such as the ballistic current may be as important. Therefore, we are motivated to investigate the ballistic current and see if we can, have a method to compute it from the first principles. So just to remind you, the ballistic current comes from the diagonal contribution of the density operator. And in order to have some non-vanishing current, we have to have some asymmetry in the momentum distribution. And this asymmetry can come from some additional scattering mechanisms. And there are two ubiquitous scattering mechanisms for every material. Basically, they are phonons and the electrostatic interaction between electrons and holes. And indeed, there have been some earlier works that discuss the contribution of each mechanism and their contribution to the ballistic current. But as I said, they heavily relied on simple models and empirical parameters. So it's hard. So first, we don't really know if we can use those expressions for first principles calculations, and then we don't really know their relative importance if we want to really explain the experimental photocurrent. So the goal of our work is really to find an expression that we are confident that we can use it to do the first principles calculation. And then we will do some numerical calculations for real materials. So that's the goal. So to do that, we have to have some theoretical framework, and we first rewrite the expression slightly so that the physical meaning of the current is more manifest. So basically, we rewrite the distribution function, the diagonal part of the density operator, as the product of the carrier generation rate multiplied by the momentum relaxation time. And we also make the band indices and the crystal momentum explicit. From this expression, you understand, you can tell that for the band velocities, they are antisymmetric for k and minus k, and all the other quantities besides this generation rate will be symmetric. So in order to have some non-vanishing charge current, you will have to have some asymmetry in this carrier generation rate. So it has to be, so at k and minus k, they have to be different. So then our main task is to evaluate this rate, this carrier generation rate, gamma, and show that it indeed has some asymmetry in the k and minus k. Okay. So how do we get this carrier generation rate? We can start from the linear response theory to compute the energy that is absorbed during the photoexcitation, and from the linear response theory, you can get this. You can show that the absorbed energy is proportional to the susceptibility tensor to the electric field. And then if we assume that each absorbed photon can be converted into an electron hole pair, then we can get the carrier generation rate by simply dividing the absorbed energy by the photon energy. So, and we still within the framework of linear response theory, we know from Kubo formula that the susceptibility tensor is basically proportional to the retarded momentum or current correlation function. So we need to evaluate this correlation function, but this is not that easy to evaluate because now it's evaluated under the full Hamiltonian, the full interacting Hamiltonian, including any additional interactions that you want to include. So we have to do some perturbative work to kind of evaluate this correlation function. So I have secretly transformed the retarded correlation function to the imaginary time Green's function, and they can be connected via the analytical continuation, and this might be more general because this can be used in finite temperature, whereas for the retarded Green's function, it is only applicable in the 0 Kelvin. So we want to do some. So we can first express the momentum operator in its second quantized form. You see these correlation annihilation operators here. And then we want to do some perturbative expansion for this correlation function. And if you really perform the time-dependent perturbation theory, let's say to the lowest order, you will end up with this very long expression. And still, I did another secret thing. I transformed from the Heisenberg picture to the interaction picture, but that's not so important. What is important is that you need to apply Wick's theorem to really evaluate this, this big correlation function. Or equivalently, you can assign some diagrammatic representation to each component. For example, this pair of operators and this pair of operators comes from the second quantized form of the momentum operator. And because you have some interaction, you will need to, you will have some extra terms, which can be graphically represented in this way. And then your job is really to exhaust all the possible ways of connecting these diagrams and only keep the fully connected diagrams. And that will give you some perturbative terms for this perturbative expansion. So that's basically the general theoretical framework. Now that we can move on to more specific scenarios. Okay, so first we consider the scattering from the electron phonon coupling. And as I said, we will only care about the lowest order contribution, which for phonon is the second order interaction. And I think Feliciano talk about this on Wednesday. Electron phonon coupling will vanish. So we will focus on the second order electron phonon coupling interaction, and we just exhausted all the possible ways of connecting those these components, and we found that in the end there are only 3 diagrams that will modify the optical transition. And only this diagram will give you some asymmetric scattering. I skipped all the reasoning, all the analysis, but if you believe me, I hope so. You will end up with this diagram, which will give you the asymmetric momentum distribution. And there is a very clear physical meaning of this diagram. This basically means that there exists effective interaction between the electrons and the holes via the exchange of the phonons. So now we apply the Feynman rule for this diagram, and then we can get some, expression that we can use for further analysis and for further calculations. So that's what you will end up with if you apply the Feynman rule, which is quite a monster expression. And but if you compare it with the earlier work, which is based on the two-band model, you can see that it essentially have the same structure. Another nice thing about this expression is that all the ingredients, all the components here can be evaluated from first principles, such as momentum matrix or velocity matrix, the electron phonon coupling, the band energy, and the phonon energy. So this can all be obtained from either density functional perturbation theory or density functional theory. So we can use this expression in combination with the Boltzmann transport equation, the expression for current to compute the ballistic current coming from the electron phonon interaction, and we term this contribution as the phonon ballistic current. But before we do that, we have to solve a technical difficulty if we want to really evaluate from first principles. That's the existence of these principal part integrals. This could be very problematic, and why? It's just, so this is just a definition of the principal part integration for one dimension. It basically means that if in the integration region there are some poles, you will just skip this poles when you do the integration. And why it is problematic for numerical evaluation? We can appreciate that from this simple function 1 over x minus 1 integrated from 0 to 3. And that's the basically how this function looks like. You can see there are two divergences when it approaches the pole x equals to 1. And if you really try to evaluate this expression, first you can do some analytical integration, which is quite simple. It's basically natural log 2, and you got 0.69 something. So you can get some finite results for the analytical results. And the reason why we can get some finite result is because the divergence at here and here can cancel each other exactly. But this is not so true for if we do the numerical integration. For example, if we choose a numerical grid that is slightly shifted towards the left, you will get minus 99, which is far away from the true answer. Similarly, if you shift your grid to the right a little bit, you will get 100, which is also far away from the real answer, but it's in a different sign. And if you're unfortunate enough to choose a grid that happens to have a grid point that lies in the pole, you will get a infinity, which is really meaningless. So we have to find a way to deal with this technical difficulty if we want to really evaluate this carrier generation rate. So how did we solve this difficulty? So basically, we first look at our expression, and we realize that all the possible integrals can be cast into this simple form. There are a function of k at the numerator, and there's another function of k at the denominator, and this minus p will basically dictate where the poles are. And then we have a numerical grid, and we split the integration into each grid, into each integration region. And if the region is small enough, then we will feel comfortable to do the Taylor expansion for both the numerator and the denominator. And if you look at this expression, you will realize that there are really only two forms of them. So basically this one and this one. And the good thing about those integrals is that they can be performed analytically. So this analytical integration should be able to solve, should be able to eliminate the numerical instability in the principal part integration. 3 minutes, okay. So I will skip the benchmark here, and I will just tell you something about this numerical results. So here I'm showing you the ballistic current on the left and the shift current on the right. You can see that they are quite different, But what might be more significant is that their magnitude are very similar. So that basically means, okay, the ballistic current might indeed be very important if you really want to interpret the experimental photocurrent. So then we want to compare with experiments, and so that we will focus on this region because we have the experimental data in this region. So that's the zoom in of those regions, and I want to remind you, or I just want to tell you that here we're showing you the response tensor of the current, not really the real photocurrent. It's independent of the light intensity and also independent of the light penetration. So we have to compute the absorption coefficient, as well as we had to know some experimental parameters so that we can really compute the real photocurrent. And after we consider those factors, we can get the current that can be directly compared with experiments. And here I'm showing you again the comparison between the shift current, theoretical shift current, and the experimental photocurrent. And you can see there's a relatively large mismatch. If you include the ballistic current, you can see that the agreement is improved, especially at the band edge. The mismatch has been partially filled. So that's really inspiring, because now we can basically prove from our numerical calculation that the ballistic current is as important as the shift current. I mean, we have to admit that there's still some discrepancy here, especially at this range. So we are motivated to further investigate if other scattering processes could also contribute to the ballistic current, so that it can further improve the experimental, the theoretical description of the bulk photovoltaic effect. So we move on to study the electron-hole interaction, like this electron-hole interaction via the Coulomb interaction. I don't have to say too much about this because it is well known that this effect will give rise to the exciton effect. But I want to emphasize that this electron-hole Coulomb interaction was assumed to be the dominant mechanism for bulk photovoltaic effect. So in this paper, so we want to examine if this is true or not. So we can do the similar things as we did for the electron-phonon coupling. Basically, we evaluate all the possible diagrams that are appearing in the perturbative expansion. But for the Coulomb interaction, because of the divergent behavior, we are no longer justified to only keep the lowest order interaction. So we have to, in practice, we have to include all the possible diagram, all the orders of the diagrams, and we have to sum them up. And luckily, we have a way of summing them up, and they can be represented in this expression, which can be solved from numerically. And basically, we'll give you a renormalized momentum matrix, which you can use to compute the asymmetric carrier generation rate. Okay, and there's another method which may be more natural for many audience. So because we know the electron-hole interaction will give you exciton state, once we know the exciton state, we should be able to compute the transition rate from the Fermi's golden rule. And if we divide the transition rate by the total volume of the system, we should be able to get a carrier generation rate that we need to use in the ballistic current expression. And if you express the exciton state in the basis of in the transition space, then you can slightly rewrite this expression, and you can see that you can still decompose the carrier generation rate into each K point and electron-hole pairs. And if you compare the transition rate with the rate without the exciton contribution, you can see that this expression is symmetric at K minus K. It's very easy to prove this. So it is really this combination coefficient, this so-called exciton wave function, that will give rise to the asymmetric momentum distribution. So basically, we will just solve the Bethe-Salpeter equation, and yeah, we'll just skip this. I think many of you are very familiar with this technique. This is all done in the Berkeley GW. So I'm showing you some first principles results still for barium titanate. The result here is obtained from the diagrammatic method. You can see that they still have very different line shape than the electron-phonon ballistic current and the shift current. But the most important thing is that if you look at the scale, it's really in a different scale. It's actually 2 orders smaller than the phonon ballistic current. Oh, by the way, I want to tell you, we just termed this current called exciton ballistic current because it's so related to the exciton. So this basically tells us that at least for this material, the exciton ballistic current is much less important than the phonon ballistic current and the shift current. And but we know there may be stronger exciton effect in 2D materials. So we move on to a 2D, very famous 2D material, MOS2, and still we computed the exciton ballistic current for via 2 methods. You can see that it's becoming larger, but it's still much smaller than the shift current. And because they are larger, the 2 methods, and you can find the correspondence of the 2 methods for these peaks, even though that's still very different. And that's expected because these two approaches took very different approximations. Okay, so just to briefly summarize what we have done, we developed a framework to compute the ballistic current from first principles, and our numerical results show that the phonon ballistic current could be as important as the shift current, whereas the exciton ballistic current is less important. And here are the citations that the publications that we made. And in the end, I want to thank collaborators, like they're all my colleagues in the RAP group, and without them, it's really hard to finish these projects. And I want to thank my advisor, Andrew Rapp, who really nominated me to become an invited speaker for this workshop. And I also want to thank the funding agency. So with that, I'd like to thank your attention, and I'd like to take any question. Thank you.
Thank you. Thank you so much, Anbang. Other questions?
I'm not sure I understood correctly, but it seemed like you were assuming that once your excited electrons were scattered once, they would stop carrying current. Well, it seems like it'd be possible that, your excited electron could be promoted and then scatter, but continue to carry current.
Yeah. So there are actually 2 types of electron phonon scattering in our like theoretical framework. One is the coherent scattering, when that it will appear at the same time of the photo excitation. So these 2 types of excitation will come together and coherently form this asymmetric momentum distribution. And after this scattering event, then there will be further scattering that will give you the momentum relaxation time. So yes, there are two scattering events here.
So are you following the excited electron all the way down until it gets back?
No, not really, because we think because the reason why we can see a ballistic current is because of the asymmetry in the momentum distribution. So we only consider the time where there is still some asymmetry in the momentum distribution. So, but in reality, once the distribution function thermalized to be symmetric, it can still be far away from the band edge. So the time scale is different. So
you are calculating the time it takes for it to symmetrize.
Yeah, that's right.
Okay.
That's right.
Okay, thanks.
Mm-hmm.
No questions?
So I guess this is a very basic question. For example, let's take the phonon scattering, right? You draw the diagram and then you have the sum over all the phonons and all the wave vectors, right?
Yes.
But then what breaks the symmetry?
Oh, so first of all, the system doesn't have inversion symmetry. And because you have light excitation, that will break the time reversal symmetry. So those basically 2 factors that will make you have a current.
Okay, so then it has to have the structure has to be asymmetric so that there's a hope that the scattering will be asymmetric.
That's right. That's right. Your system has to be non-central symmetric in order to have this bulk photovoltaic effect. Yes.
Okay, thank you.
Sure. There's no Zoom. There's no question from the Zoom.
Okay, so then let's reconvene at 11:15. Thank you so much for Come back, everybody. Okay, let's start the session again. So now we're very happy to have Wojciech Blaszczak to tell us about dynamical electronic correlations from models to materials.
Okay, so thank you very much. Hopefully you can hear me. It's okay. Okay. So there's a slight change in the title that's probably not reflected in the program. But nevertheless, I would like to introduce, or I'm very happy that I was invited, and I want to thank the organizers for inviting me to talk about the stuff that we've been doing with my group. And we are focusing mostly on dynamical renormalizations and fluctuations in quantum systems and how they actually change our description of quasi-particles. And today I would like to take you on a bit of a route from models where we will try to understand how many-body perturbation theory and diagrammatic methods help us to understand and improve the description of excitations, to something that we do on real materials, and we are using some methods that we are developing that are based on stochastic samplings and that allow us to work with extremely large systems. So just to give you an overview, so when I talk about quasi-particles, I will have a very narrow definition of that, and I will be talking about quasi-electrons and quasi-holes, essentially the stuff that you can observe by photoemission spectroscopy, where you shine high energy and you can discriminate its wave vector and energy. So that your observable, something that you can truly measure, would be the single quasi-particle state in the sudden approximation. That will be the spectral function that has the wave vector and the energy here. And then I think you did from the knowledge of the Green's function that describes the propagation of the quasi-particle in the system. So essentially something that gives you a time-dependent probability amplitude of adding a particle in your system and then removing it later on, from the system. And maybe some of you pair with the Green's function approaches and Green's function methods. So if you're wondering, is there something really a nice textbook to use, then I would just refer to the previous evening and say, well, there is a textbook that everybody in the field is nowadays using, and it's quite amazing that in like only 6 years since it was published, it became one of the major textbooks for this field. So when I talk about dynamical effects, there will be essentially two relatively trivial things that one can understand when looking, for instance, at this actual photoemission spectrum of graphene. So what we see is close to the Fermi level, we have very sharp peaks, but as we go to higher and higher energies, we are losing the intensity, and there's this lifetime broadening. Right, and that is relatively trivial to understand because we create a hole and at relatively high energies, and there are many more ways how to essentially dissipate this energy, and the hole will have a renormalized, will be a quasi-particle, and then it will actually coalesce to the Fermi level later on. The other things that are kind of more interesting are all the satellite features in your spectra that encode all the additional couplings, because you can imagine that you smash your system with a high energy photon, it creates a hole, but it can also create many additional excitations in your system, and they will be also encoded in your photoemission spectrum. So those are the some of the dynamical effects you may be interested in, and you want to develop some first principles description of these things in order to know more about your systems. So what we usually do, we are thinking about a propagator theory, and we can write this geometric series that essentially describes a scattering process where we have some reference Green's function describing some, let's say, non-interacting or propagating through the system, something I know how to solve. And formally, I can just repeatedly scatter through the sigma, which we call the self-energy, that will be some complex valued, non-local and dynamical potential that actually describes all the scattering mechanisms that are in the system. And again, I will just narrow down the definition. So we have talked, or we have heard talks about electron phonon couplings and other things. So all of that can be hidden in the self-energy, but I will just look at electron-electron interactions today. So if you want to resolve where the poles, where the self-energy, where the spectral function has its maximum, where the poles of the imaginary part of the Green's function, you can write down an effective single particle equation that doesn't look too far away from what we know from DFT or Hartree-Fock, where we have all single particle terms here, the single particle Hamiltonian, maybe was the Hartree term as well. Here we have the quasi-particle energy. Here we have so-called Dyson orbitals that will be, something that we cannot properly normalize to get a probability, but something that looks like the true orbital of an electron or a hole in the system. And here is our self-energy. So now, how to get the self-energy and how to get it better is one of the main questions. Today I would like to maybe talk a bit about how to quantitatively predict the quasi-particle energies and how to improve the methodologies that allow us to essentially derive the expressions for the self-energy in the limit of what we call weak and moderate correlations. And I just want to, a word of caution, the weak and moderate correlations do not mean that there are essentially no interactions. We'll see that there are many interesting effects happening. But also, once we know how to do that, maybe better, then we can also ask the question how this can help us to understand better something about quantum materials. So I would say that, if we are in the regime where this scattering is relatively weak, then we can use, the tools of quantum statistical mechanics that take 60 years. Already when you look at Kadanoff and Bain, essentially everything is up there. And then it was later formalized by Hedin in this formalism of integral differential equations that have to be solved self-consistently. In practice, the self-energy essentially diagrammatically is written in this particular form, was a convolution, space-time convolution of the Green's function, and screen-Coulomb interaction, and in famous vertex correction that I will be talking about a bit more today. So essentially, the scattering process means that I have an electron that releases a virtual plasmon or charge density oscillation in the system and then reabsorbs it. And that's how I want to describe all the dynamical effects, all the dynamical fluctuations in my system. This reabsorption is renormalized by this vertex correction, and usually it has been neglected because it just adds to the complexity of what we can in practice compute. If we now look into what is the actual equation for the vertex correction, then we end up with something that is, again, a recursive series that essentially very much, is equivalent to the Bethe-Salpeter equation that just tells us essentially that it contains interactions of electron and holes or electron-electron interactions as well. The simplest term is just an identity. So it means that I'm reabsorbing my plasmon, and that will be the simplest and the lowest order expansion that will be the GW approximation. But now we want to understand a bit better what this interaction kernel is and how to maybe include high order terms and improve our description. And it turns out that this interaction kernel, the same way as it is in the Bethe-Salpeter equation, is just a functional derivative of the self-energy with respect to the propagator itself. And today I will just very briefly talk about, how we can get these descriptions better and how we can understand how to include higher order interactions in this way. And you can see a very nice connection also to DFT, where essentially something like a functional derivative of a potential that describes electron-electron interactions with respect to the main quantity that will be the density, which is just an equal time and diagonal part of the Green's function, will be the exchange correlation kernel. So the problems are here very much related to what we have heard about TD-DFT in some of the previous sessions. So conceptual questions in this first part of the talk will be essentially, okay, I have in principle the set of integral differential equations that I need to solve self-consistently. I realize that because of this functional derivative, every time I essentially enter the loop, I will generate a new self-energy, and I in principle should update my kernel. And this leads to a series, an ever-growing series of expressions that I have to account for. So I need to think about how to conceptually truncate this, ever-growing series of equations, and how to probably truncate it in the best possible way to get good agreement with, let's say, exact solutions for some model systems. And then the next question will be, okay, if I do it, I want to see how these interactions actually affect my spectral functions. And that's something very important when I want to look at materials. So I will start with model systems because they are, something we can compute exactly. illustrate something, and then I will show you about how we do some implementations for real materials. We'll start with molecules and then something bigger. So again, I would just go back to this kind of Baeyer-Salpeter equation. I just remind you that the vertex, the kernel of this vertex is this functional derivative, and in principle, this should contain essentially derivative with respect to three quantities that we had before: the Green's function, the W, and the vertex itself. And this last, and that generates a set of essentially kernels. The K0 would be just the identity. And this one has been universally neglected up to now. What we can see is that, if I start with the identity, I get this GW approximation that only essentially accounts for charge density fluctuations. I add the particle to my system, it generates charge density fluctuation, and that will describe, it's very classical in a sense. It just describes how my system reacts to that new charge particle in the system. And here I'm plotting the spectral function as a function of interaction for a Hubbard dimer, a very simple model that has been used ad nauseam to just illustrate how perturbation theory fails miserably its strong interactions. What you can see is the spectral function has from the exact solution, two main peaks. It has actually four, but they are symmetrically around the Fermi energy. So we are just showing one portion of them. The main quasi-particle peak that is here, its position is just divided by U so that we have this nice plot. And here is a satellite peak in the gray shaded area. And if you start with Hartree-Fock as the lowest order approximation, you will get those shaded triangles that are here. And if you do GW, what you will get is essentially here, okay, here you improve. That's the only point where you're getting something right, but everything else is essentially deviating from the exact solution, which is kind of expected. I mean, Hubbard dimer is definitely not dominated by screening of some charge density oscillation. It also gives you something about the satellites, but they're completely off, and there are many of them. Now, okay, so what I can do next is to essentially start to generate the next corrections with the vertex correction, including electron-hole interactions. And we can see that really nothing much is happening on the main quasi-particle peaks. Something is happening with the satellites. The reason being that we are essentially removing part of the self-interaction error, that is or the self-polarization error that is known in GW, and that is mostly also shown in the satellite positions. And now we are including exactly the coupling to electron-hole pairs. And in this is fully self-consistent solution with the lowest order diagram that I'm showing here. Okay, we can go further and we can ask, okay, if I start to add even more, even better things, okay, what will happen? And you can see, well, I will start to add some diagrams, and that's where, the most advanced theories have really stopped, was adding the diagrams of these types, where essentially those experts in the audience recognize T-matrix-like expressions, and you will see it completely changes the asymptotics, but that's not really great either. And what we, can add on top of it, unlike anybody else, is essentially add those derivatives with respect to the vertex correction. And they improve the thing a bit, okay? We can still see that maybe we have improved up to this point. It's just, a lot of work. And what is the result? I mean, still very weak interactions. Now, this is a truncation at the level of all of these diagrams, right? At the very lowest order. And now we can say, well, I will take those diagrams and do functional self-consistency, put it in Hedon's equation, and include this last bit, which is the functional derivatives of the vertex itself. It turns out that essentially those lowest order diagrams are, of course, insufficient, but this kernel is responsible for generating all the other interactions. If I neglect it, and as it was done previously in the theories, you wouldn't be able, essentially through the functional self-consistency, to generate new types of interactions. But if you include them and essentially run everything self-consistently and do the resummation till infinity, you will get this green curve, which we were kind of happy because you're getting up to interactions. Let's say U = 5 is still relatively okay. So in other words, we believe, that the story for us was, okay, maybe the perturbation theory, if we executed how it should be done with all the functional self-consistency treatments, can really push us towards a better prediction of quasi-particles and towards more accurate description of things. So, okay, so now what? This is a small lattice model. So how do we apply it to real materials? And you realize that all of these diagrams, are very expensive to evaluate. So we have to do what we have to invent or develop is some numerical algorithm that will help us to solve it practically. So if I want to go from models to materials, and I put materials in quotes, because I will start talking about first molecules, which you can consider to be materials, but those are mostly test cases, then I really have to start to think about many electrons to deal with. So the usual, the starting point Hamiltonian is usually not a problem. I can do DFT and Hartree-Fock and for relatively large systems. But when I want to evaluate all, if I'm happy even with the lowest order diagram that I'm showing here, that's the GW, you will realize that it scales as n to the fourth with the number of electrons. And the reason for the cost is kind of intuitively clear, because I need to take care of propagation of all particles and holes through the system that is described by the Green's function, and essentially propagation of all charge density fluctuations that are hidden in the screen-Coulomb interaction. And as my system grows, the information that I need to essentially take care of is bigger and bigger and bigger. However, the key point is that all of these, charge density fluctuations and all of these things are collective modes of my system. So they're kind of amenable to some low rank representation. And indeed, there has been in the past few years, there has been, some push on doing low rank representations for GW by Giulia Galli and others, but also one can try to do something in the time domain. What I would advocate for is a kind of a different approach, which essentially, instead of characterizing the low rank representation of these correlators, essentially recast the self-energy as a statistical estimator. And what we do is, instead of evaluating our Green's functions, W's and vertex representations in the basis of a single particle states, as we should normally use, and that's what you find in the textbook, we will actually use some random orbitals that are essentially in the single particle or single quasi-particle Hilbert space that is known to us. That's actually because we are doing perturbation theory. It's known from the spectrum of the H0 of this non-interacting Hamiltonian. And then use some random states that essentially span the entire subspace. We can filter them. We can filter those that are in the occupied subspace and those that are in the unoccupied subspace, propagate them backward and forward in time, and essentially start to get information about propagation of particles and holes. And how does it work? Well, so as I said, we are propagation of electrons and holes through these random vectors, and W is actually rewritten as a induced charge density fluctuation that we are sampling. So here's a simple movie. If you have a small molecule, you can look at a sampling of this charge density fluctuation. It turns out that, as I said, most of these things are amenable to low rank approximation. And in practice, it means that you need only few samples to really get all your main modes of propagation of these interactions in the system. So you go from n to the fourth, or polynomially scaling things n to the sixth, if you include vertex corrections, to effectively something that we observe to scale linearly with the system size. And it's all due to the fact that we are looking at those collective modes of interactions. And the fact that we are using random vectors also allows us to actually, make a code that very easily is embarrassingly parallel, and you can submit it to a large HPC cluster and essentially take all of these samples on individual cores. So we have already done the GW, and my group has extended it to the vertex corrected GW gamma. We have extended it to 0D, 1D, up to 3D systems, various applications. And the largest system that we have done, previously with deterministic methods, maybe had a few hundred electrons. Now we're talking about 13,000 valence electrons. That's this paper, I believe, which is about 10 hours to time to solution. So that is very efficient. Okay, so here are some examples of the problems and systems we have looked at so far. So some photovoltaic systems, some coupling to plasmons, even disordered phases where we are doing some orbital reconstruction and simulating photoemission spectra of molecules in water, and a lot of effort has been done on quantum materials and quantum defects for quantum information science. So, okay, so we have a good methodology. So now we can push on in two directions. One is to try to do something more accurately, that I will show something that we understand, I believe we understand better about the vertex corrections. And then I will give you one example of our application to one of the quantum materials that is kind of huge in terms of its size. So dynamical correlations and where the vertex corrections play some role. And I showed you, this Hubbard dimer as an example. We can look at that. But here I will start to work with some real molecules, and that will give me maybe a better benchmark. So here I'm looking at the vertical excitation for electron affinity of hexosine molecules, so relatively large if you ask anybody in the field. And this is coming from a benchmark that Jeff Neaton's group did in Berkeley for the best estimates and possible errors in GW. So this one is the coupled cluster. They estimate the best electron affinity for hexosine. And this is where you start with the DFT. Not too bad, but relatively far. Now you start to add those many-body corrections on top of it. And what you realize very quickly that it actually deteriorates. It goes in the wrong way. And you can say, well, it's maybe because I'm not performing perfectly with my W, because I'm taking a random phase approximation. Again, for those for experts in the audience, I can remove that constraint and essentially do something fancier and schmencier, but it gets even worse, okay? And now what happens here is that if I add the vertex corrections, and they're unscreened vertex corrections, so not properly renormalized, it immediately shifts me here. And we know that if we properly renormalize the Coulomb interactions in the vertices, it will get us actually very close on top of the couplet cluster. So one of the reasons why vertex corrections are interesting is because they remove the self-polarization errors that are mostly, and they dominate the errors for the unoccupied state. So that is one good reason to use them. And again, you can parallel it with self-interaction errors in DFT that we know also plague the description of unoccupied state. So there's some parallel here. What is even more interesting is that when you look at a comparison of photoemission spectra, and you go to very high energies. So here we were doing a benchmark test against full CI. So we have done essentially a selected CI, about 100,000 determinants, inverted everything and got the spectral functions and compared GW gamma and this selected CI results. We were able to do the CI only for very small molecules. So that's why what we have here. And that's why I put materials in quotes, because any material scientist will laugh at us, or they do actually, but that's fine. So here, essentially the first message is here that the mean absolute deviation from the full CI result is always lower when you add the vertex correction. That is not too big of a surprise. It was already motivated by here. But if you look at this graph, I'm just showing the correlation between, the excitation energies. This region we call SQP and this MQP. What is the difference? The SQP region will be single quasi-particle regime. You shine light, you excite, you create a hole in the system, and this will be your one quasi-particle. Here at the high energy limit, you're essentially getting to the regime, which from the 80s was called a complete breakdown of the quasi-particle picture, because you essentially have energies of photons about more than 20 electron volts. You smash to your molecule and you create a lot of excitations. And so we kind of challenge that notion and we say, well, it's not a complete failure of quasi-particle picture, but it's just a regime where we have multi-quasi-particles generated by this interaction. And now the very nice thing about those vertex corrections is that they allow us to couple these fermionic and bosonic excitations where we have electron hole pairs that are also generated at these high energies to actually describe them from first principles for the first time without making any ansatz about the Green's function itself. So here's a comparison in the brown area. We have the full CI solution. GW is these orange peaks, and the green one is the GW gamma. So, okay, we get a much better description of the main quasi-particle peaks, but also we are getting this forest of additional peaks that essentially describe this multi-quasi-particle generation. So what we want to say here is that this complete breakdown of the QP picture is just really transition into multi-quasi-particle picture. So how do we reconcile this thing about vertex corrections? I'm telling you how important they are with what is well known in material sciences, and that's from Mark van Schilfgaarde's paper already some time ago. That if you look at most of the solids that are labeled here, and you look at LDA versus GW, and we know it, GW works excellently well. So when do we need to have vertex corrections? So from what we have learned and what we think is that the vertex are likely necessary if you have a very confined system or you're strongly coupled to some dominant collective modes of excitations where you have multiple dissipation channels of energy, and you need to include it already at the level of the self energy itself. And Probably for the chemists in the audience, it's not surprising that those are exactly the molecular systems that I have described before. And in these systems, also screening is not likely the most dominant many-body effect. For everything else, one can argue that simple and conventional GW, and simple in quotes, is probably enough. And if we have some correlated physics, it will be mostly dominated by some local effects, local, let's say, in energy space or local spatially. So that will be a regime where we want to do some embedding. So how am I doing on time? Okay, so I will just very quickly, okay, so I will just very quickly, it's a California session, so it's relaxed, so that's fine, so I can take more time. So I will just, I will not continue with the vertex corrections because we started to apply them to solids, but show something that we have done exactly for this regime where you need to embed some strongly correlated problems. And one of the problems that we worked on, or we were asked to work on by our colleagues, was to look at the screening in twisted bilayer graphene. And I will just motivate it in a second why that is at all interesting, because twisted bilayer graphene is one of those things that everybody talks about and usually in connection to strong correlations. And this, for those who want to see more details there in this paper. So, okay, we go from monolayer to bilayer. It's relatively trivial. We just have, the dark cones at the K point, and here they are trivially gapped. And now if I go to a twisted bilayer, I will, if they were completely non-interacting two monolayers, I will have essentially a degeneracy of my direct points at this level. However, they are actually in practice interacting, so they are gapping and creating those very localized states. And whenever I have a strong localization of electrons, that's kind of works as a precursor for strong correlation. And indeed, if not me, but my colleagues who can do it, if they construct twisted bilayer graphene with a particular, twisting angle around 1.1 degrees, they will see, essentially all the hallmarks of correlated physics, because when they start to measure the conductance of the system versus the carrier density as they dope it, and when they reach the limit of half filling exactly per the Moire cell of this periodicity, you will start to see strongly insulating states, and adjacent to that, superconducting state. So that really tells you something about, okay, we have driven the system from very weakly correlated to something that is strongly correlated. The thing that is interesting is that you can externally, there have been nice experiments done, you can externally apply different dielectric environments, and actually by changing the amount of screening, you can drive the system back and forth between superconducting or insulating and so on. So what we conclude is that if I look back at my Hubbard models, and the models were in the title, right? So I'm always going from models to materials. I can think about that, the fact that there is a strong competition between my hopping or kinetic energy terms and my Coulomb terms. So now, oops, the next question that our experimental collaborators had was, is twisting the only control knob we have? Well, not, and I think it's close to home because Matt Yankovitz here with Corey Dean's group and Columbia, they have done these beautiful experiments where they have shown that you can get away with much different twisting angles, but by applying pressure, you will essentially, again, create a strong coupling between those two monolayers. And again, in the measurement of conductance, you will start to see these big dips that essentially indicate mod insulating regime. So our question was very simple. Okay, is the behavior upon twisting the same as the behavior upon compression? So for this, we have started with a very, very large, system, but yet, only 6 degrees twist. And the reason was twofold. First of all, this is definitely weakly correlated in ambient conditions. But second, we have some experimental data that we can, validate against. And just for those in the audience who are interested in how big the system was, this is the periodicity, 2.34 nanometers. And we had to use some supercells. So in total, we had about 10,000 electrons. And the strategy is, again, to use stochastic many-body perturbation theory and to use some downfolding on some effective models for this strongly correlated subspace. I will just show that, validation worked really well, and it tells you that, when you are in this zero pressure, that, GW is really fine in this case. The agreement with experiments is within 10 MeV, so that's pretty okay. And then we have started to compress the material. And as you go to very high pressures, you indeed see that you start to localize your states in some portions in the AA stacking region of your bilayer. And if you look at the densities of states, DFT and fully self-consistent GW that we performed here tell you a very different story. DFT essentially tells you that the gap of the system starts to close and you will have a lot of hybridization, but GW essentially tells you, oh, all my weakly correlated states are just simply shifting in energy, they don't care, and then something is happening at the Fermi level. So if you do the analysis more closely, and we have implemented all of that stochastically, so we were able to treat these large systems. So we have used fully self-consistent, quasi-particle self-consistent GW. Then what you do as the analysis of what is happening around the Fermi level. And here the important message is in this cartoon here. We are plotting the Dyson orbitals that we get from the diagonalization of the quasi-particle Hamiltonian in the basis of our DFT orbitals. You see that most of the standard weakly correlated states are kind of diagonal here, nothing interesting. And the strong interaction is really happening for those 8 states around the Dirac points. And now I will just very briefly go over what we have done for that. So we have essentially taken those strongly correlated states, downfolded onto a Hubbard model for which we essentially evaluate all of these T and U terms from ab initio calculations. The hopping term, it pretty much describes the same kind of physics that you have in magic angle twisted bilayer graphene. However, now for the U parameter, if you start with the Baire-Coulomb interactions, you will see that essentially the U shoots up. I mean, you're localizing your states more and more and more. So you have, flat bands and strong interactions, so it's highly insulating state. But what we have to bear in mind is the fact that we are actually in an environment of highly polarizable medium. So we have all of these weakly correlated states that screen our interaction. So what we do is we essentially compute, we compute now these U terms that are essentially screened by all those weakly correlated electrons. And for that, we have again used stochastic methodology to really do constrained RPA calculations. And very quickly, that will essentially give us this frequency dependent U terms. And now you can see that how this frequency dependent U terms look. They essentially, as you go from 0 to 100 GPa, they show some symmetry breaking and so on. What I want to point out is the accuracy for 1 MeV, convergence of the stochastic error is only 200 samples, so very, very efficient. And the bottom line of the story is that essentially screening, as we have seen, increases, but due to the gap opening that we have seen in the GW, or the fact that the gap does not really change with high pressure, we are not really seeing any strong renormalization. And in other words, we still, for the flat bands region, where the T roughly is U, so around 25 to 30 GPa, we will really not see any kind of interesting physics. And for the regime where we have flat bands and strongly localized electrons, we have U over T roughly around 7. So strongly insulating regime. So the bottom line of the story is, this question was, is the behavior the same up in twisting and compression? And I will just, skip to the end and say, well, no, we don't think so. But high pressure induced effects are very distinct from those that are induced by twist, and they probably favor those strong insulating regimes. Unfortunately, I don't have an answer whether that's correct or not, because it discouraged our experimental collaborators to perform any experiments on this. But if that is a success, then maybe. But for us, the main point was that we have developed all this methodology to compute it. I will skip our work on the downfolding. We can do very efficiently these things without 10 to 20 CPU hours. So within an hour, you can get dynamically renormalized Hamiltonian models. And some of our observations is that we can systematically build this perturbation theory to really push the convergence radius of the perturbation theory to strong interactions. The dynamics of the weakly correlated electrons is actually quite important to drive certain phenomena, even for what is nominally considered a strongly correlated material. And what I'm strongly advocating for are the stochastic methods, because as I have shown you, we can do something for 10,000 electrons within hours of computer time. With this, I would like to thank my group, especially my postdocs, Maria and Carlos, my graduate students, NSF DOE, and for your attention.
Thank you. Thank you so much. Are there questions?
Thanks for a really interesting talk. So I just had a question about the TBLG. So in the
Mhm.
end, was your interaction, you seem to write that you were using the omega equals 0 limit of the interaction.
So in this case, we were looking at a static limit. When we looked at the frequency dependence there, it was so, because it's a very low energy physics that you're looking at, you're still at the very close to the 0 frequency. So the static limit in this case is arguably probably okay. If
Thanks.
that answers your question.
Yeah.
Mhm.
Thanks, Vitek, for the very nice talk. I have a question on the vertex correction on the, was that a Hubbard chain dimer or?
It was a Hubbard dimer.
Dimer.
It was a Hubbard dimer because well, we were choosing something that was very known in the literature to show the main problem. So we have some other systems that we have in the paper. If you look at it, there's an extended discussion here I'm showing.
Right. So my question is, why do you expect the, I guess you're still using a quasi-particle approximation, right, in the sense that you cycle, but you still assign a single quasi-particle peak to your Green's function. Is that the case? So the question is, do you expect the satellite feature should also be included in the self-consistent?
So
feature?
when we
Is there
do
a
the
way to do that?
self-consistency, we compute a full matrix for the Green's function and always invert the matrices. So we're not invoking necessarily the quasi-particle approximation.
But by quasi-particle, I mean your G of omega. I guess you assume there's a single delta function there.
Yes, yeah.
So do you anticipate that satellite features in G of omega could be important in the self-consistent procedure as well?
Well, we maybe I don't understand the question fully. They appear due to the inclusion. So the satellites already appear at the GW level, and then as you include more and more of these vertex corrections, they actually improve the description of these satellites. But what we know is that the perturbation theory actually describes this kind of recursion of scattering processes that usually lead to many of the satellites to appear in this model. But we know from the ED solution there should be just one satellite peak. So generally there is one feature that is always wrong, as we found in the perturbation theory, and it's the exaggeration of the number of satellites that you get. Okay, but otherwise the satellites just come out of this calculation naturally. I don't know whether that was what you were referring to.
Partially, but I think that I can follow up afterwards.
Yeah. Okay,
thanks
great.
again.
Any other questions? Okay, so let's take first again. Thank you. And finally, we'll have Philippe Jornada from Stanford University.
Test. Okay. Yeah. No, that's fine. I think. Yeah. Okay, thanks so much. First of all, let me thank the organizer for inviting me here, and thank you all for staying through the end of this very nice workshop with a very nice number of talks and different topics and really stimulating with lots of take-home messages. So today I'd like to tell you a little bit of a slightly different topic. We heard a lot about single particle properties, correlation, and so on. And today I'll tell you a little bit of a complementary story on some interesting physics that emerges if you're understanding optical excitations in materials and their dynamics, especially on 2D materials. So basically, the way that I like to motivate this is that at least people are in the last few decades, the way that in material science, for instance, people think about properties of materials, that if you want a device with a particular property, you go back and look at what is the atomic structure that leads to that particular property of interest. But what I think is a very exciting different perspective that has emerged in the last few years is that the properties of materials don't have to be tied to the bulk properties. And then, for instance, you can get really nice emergent properties by driving a material out of equilibrium. And also by simply taking materials and twisting. And whether at the interface of two materials, you can have states that are non-trivial that emerges out of otherwise trivial materials. So today I'd like to touch a little bit of those two topics. I focus a little bit more on the physics that emerges on 2D materials and what kind of new physics we learn from there. As the last speaker, Wojtek, kindly enough introduced the topic, our group also focuses on first principles calculations using many-body perturbation theory and Green's function methods in particular. So as Wojtek mentioned, in general, if you are interested in one particular excitation property of a material, you can ask yourself, what is the right kind of Green's function to look into? And that Green's function will be associated with the propagation of one excitation, the poles of which are associated with long-lived excitations. So for instance, quasi-particle excitations are associated with the single particle Green's function. You ask yourself, not necessarily what is a many-body wave function, but an alternative way is to ask yourself, if you add or remove an electron at later times, what is the frequency dependent of this particular object upon Fourier transforming that, and the peaks of which will also be associated with the energy to turn an electron in or out of the system. And of course, you can write a Dyson-like equation for the Green's function in terms of a non-interacting counterpart that we typically write in terms of a constant DFT orbitals and some self-energy sigma, which includes all the many-electron interaction. In this talk, we basically use the so-called GW approximation without the vertex correction that can describe well systems with weak to moderate correlations. And you can also ask yourself how we can understand other properties, such as optical properties and excitations of materials. And the idea is very similar. You ask yourself, can I add one electron and one hole in one particular time? Can I remove them afterwards? You compute this Green's function, or how we usually call in the literature this electron hole correlation function. You can also write a Dyson-like series of that in terms of a non-interacting counterpart, L0, which does include electron hole interactions, and one kernel K, and the poles of which are associated with long-lived excitations, basically exons of your systems. So we actually right now have formalism to understand those excitations quite accurately for a variety of systems. And I like to give at least one example that is relevant for my talk, which is actually early work that I did during my PhD on monolayer materials. So for instance, if you do not use electron hole correlations, you just describe optical properties within a band-to-band picture that is known as GW-RPA, namely you take single particle excitations from the GW approximation, but you don't include vertex correction. And in the monolayer material, this kind of description gives you this red curve here, which doesn't even qualitatively describe the absorption spectrum of a system such as a monolayer molybdenous sulfide. And of course, what you're missing in this case is a very strong electron hole interaction. So you shine light, you create a bound electron hole pair. You can solve this by solving this Dyson-like equation for the electron hole correlation function. We call this the beta salpeter equation, and that gives you sub-band gap excitations that are characterized by discrete peaks known as excitons. In particular, these two series of peaks A and B are associated with spin orbit split states, and you see there's a prime, A double prime, which are associated with excited Rydberg states like 1s and 2s and so forth. I do want to mention that this interaction kernel is indeed described by the derivative of the self-energy with respect to the Green's function. There are two terms. There is one attractive interaction that is basically associated with the many-body screening, and there is a repulsive exchange-like interaction that is responsible for singlet, triplet splitting and similar phenomena. I also want to mention that you can also, from first principles, include electron phonon interactions, for instance. And that is quite important in those materials. They broaden quite a lot those excitonic transitions. And that actually describe even qualitatively quite well the absorption spectrum relative to experiment. So those methods have matured dramatically in the last even 5 years, I would say, not only for the GW calculation, for the beta salpeter calculation as well. We can sample monolayer materials, few layers materials. And also we can tackle systems which are much larger than before. So basically all those Green's function methods for GW calculations, which started in the 1980s with 2 atoms per unit cell or 8 electrons per unit cell, right now can tackle systems with up to almost 12,000 valence electrons, and even a little bit more, even larger systems, of course, if you include stochastic techniques such as what Wojtek mentioned a few years in the last talk. So there is, of course, a bunch of important development communities from low-rank approximation stochastic techniques that I'm not going to mention here. So with that said, we're very comfortable with this sort of formalism to understand, again, quasi-particle and optical excitation of materials. But in terms of frontiers, we think that there are two classes of problems which are quite exciting. One is that it involves how those excitations are modulated and modified in general if you have interfaces of twisted moire materials. And I tell you a little bit how that manifests in the way that the axons behave in those materials and what is the relevance for that for quantum information sciences, for instance. And then I tell a little bit about how those axons behave in terms of their dynamical properties and how we can understand the line width and the coherence of those excitations also from first principles. And what are some important effects that have been neglected before involving basically multi-band physics of those lifetimes. So I first go to this first part of my talk and tell a little bit how we can think about axons and those twisted systems. So what happened is the following. If you look at a system such as a monolayer molybdenum sulfide, you have a direct band gap transition from K to K. You put one layer on top of the other layer, you often get the staggered band gap. Namely, the valence band is one layer, the conduction band is the other layer, as also shown in this picture. So if you shine light, you're going to create one axon in one layer, and very quickly, either the electron or hole will be transferred to the other layer. This typically takes place in about 50 femtosecond. It's really ultra fast. But now those interlayer axons are very long-lived. For instance, in the monolayer, their lifetime is of the order of 30 picosecond. In the interlayer, axon is of the order of 100 nanosecond, which means that they can even be long-lived enough for manipulation with basically and be coherent with, say, external fields for quantum meters or even potentially qubits. So the question is, how do we think about those axons now that you put one layer on top of the other one, and there's a finite twist angle? So on the left panel here, I'm showing schematically a side view and a top view of a twisted biolayer of a transition metal dicocogenate. And the thing that I wanted to focus on is that as you transverse this moire unit cell, that is much larger than a primitive unit cell, there are several local regions that you can identify as high symmetry stacking. And if you just naively compute, say, the quasi-particle band structure locally in each configuration, what you conclude is that there is a variation of the band gap from which you can deduce that effectively electrons or holes will experience an effective potential that people call a moire potential. In those materials, this moire potential can be of the order of 100 milli-electron volt. So there's a lot of excitement about utilizing those moire potentials, because it means that if you shine light and you have those interlayer axons, they can be trapped into those low energy regions of those moire potentials. But the question is, how much do we know about them and how do those moire axons behave? And it turns out that we don't know quite a lot about them. The reason being that right now, most of the characterization and experiment is done optically quite indirectly by looking at the photoluminescence. So you shine light, see what light gets emitted, and you basically conclude that the light that gets emitted by photoluminescence has a multiple peak structure, which you can then try to fit with models shown as here, from which you can deduce that this potential will confine your levels with some sort of quantum harmonic oscillator-like behavior. So the question is whether we can actually obtain a better description and understand the physics more without relying on these very indirect measurements, and whether we can actually quantitatively obtain the size, the binding energy, and other properties of these axons. So in order to address this question, I have to go one step back and tell a little bit of what is the right way to think of those axons and also how we think about the moire axons more rigorously. So one exciton is simply a correlated electron hole pair. Namely, if you think about a two-band model for simplicity, you describe one exciton X as a linear combination of all wave vectors K as a sum of a state of CK, VK with some expansion coefficient A of K. This A of K is shown schematically here in this picture, also known as the exciton envelope picture. So this actually describes one exciton with a given Bohr radius between the electron hole, but the exciton itself, the whole exciton, is a Bloch state with zero center of mass momentum that can be anywhere in my crystal. This exciton is dispersive. So I can actually compute what is the how an exon with this final momentum, say Q, looks like. And you can convince yourself that it looks like this. If you want to have a final momentum, you displace the holes by some amount, the electrons by some other amount, and the amount by which you have to shift them is proportional basically to the ratio of the electron mass to the total mass, or vice versa. So the idea is that, of course, if you have a exon that is confined by a Moiré potential, you can now describe this exon as a linear combination of exons with different momenta with some expansion coefficient. So basically, if a free exon can be described as XQ, a exon that is confined as be Moiré potential will be written as a linear combination of these guys with some expansion coefficient C of G. And you can think about this like this. So what is important here? I hope that this picture gives you the idea that the distribution width that you have actually in the electron hole are different. And that's actually quite important because it allows us to understand quite a lot of those excitations. But in particular, this A of K is again related to the Bohr radius, the internal separation of the electron hole. And the C of G, the Fourier transform of that, is related to how much you confine the whole exon in the center of a mass frame in a crystal. So the question is now, if we have ways, even help experiment to understand how this A of K and CG looks like, there's quite a lot to learn about the localization of those states. So how can you understand this internal structure of an exon? Well, if you go to high energy physics, you can understand the internal structure of a bound state with a particle accelerator or particle collider. You hit something and then you see the scattering property, and you can deduce that from auto, the internal structure of an atom, for instance. In condensed matter, we can do the same thing with ARPAS. You shine light, you emit an electron, but if that light, this photon, can actually dissociate an exon, the point is that the photometer electron will have information about this inelastic scattering process. So how do we understand that more rigorously? Well, we simply go back and write down what is the photoemission process that is associated with this particular inelastic scattering. So people have, of course, focused quite a lot in the past of what is the photoemission property of an exon, in the sense that if you shine light on an exon, if your photon has enough energy, you yank out the electron, and that is what you can measure in your angular resolved photoemission spectroscopy. However, there's a lot of information that is left behind, particularly this hole information. You cannot directly photoemit the hole, but what you can ask yourself is, if I shine a light in the valence band, and the hole is now and there's a hole, what happens? So it turns out that if you think a little bit, then it looks like this is way more complicated in a sense that the initial state is an exon that is described as a linear combination of electron hole pair. A diagram is that it scatters to another exotonic state, and light can basically create a free electron, a free hole in the system. But this hole can also get confused with the hole that makes up the exon, and have to treat those two diagrams coherently. But if you work this out, it turns out that the expression are quite similar at the end of the day. It turns out that the intensity associated with the photoemission of an electron is nothing else than the convolution of the exon envelope function and this Moiré expansion coefficient. Likewise for the hole intensity. But there was an important difference. When you do this convolution, actually, it turns out that those Moiré reciprocal lattice vectors G are rescaled by this alpha and beta, which are precisely those mass rescaling factors that I mentioned before. So the point here is that if there are ways that one can measure the electron hole distribution in such ARPAS experiment, you can actually understand quite a lot of unique physics of those exons. It turns out that this is the perfect time to do that because there is a very recent new generation of ARPAS technique that can measure with extreme energy and momentum resolution these sort of photoemission properties. So I'm showing the left-hand panel the ARPAS spectral function basically for a biolayer of tungsten disalonide and moly disulfide if the sample is unexcited. And you can see basically the VBM at the K point, the gamma point, a little bit lower in energy and so on. Now, if you do a pump probe kind of a setup, you basically can photoemit from the electrons. And these are precisely the electrons that are attached to the exon. But if you look carefully at the valence band, you also see there is something missing here. And if you zoom in, you can actually see that what is missing are precisely the holes that are attached to the exon. So long story short, if you can combine this information that we can deduce from this microscopic theory with ab initio calculations, it turns out that it can deduce quite a lot about these extons. So basically, we perform also an ab initio beta substitute equation calculation and so on. Our calculations show that the radius of the exon is about 2.4 nanometers. We also show that the center of mass is confined by a region of about 1.3 nanometers. And with our theory, we can actually deduce from experiment what is their measured, experimentally measured radius. And it turns out that in experiment, one deduces that the confinement of the exon is about 1 nanometer and the radius is about 2.5 nanometers. So this is really, I think, a great agreement given all the details that go into getting a accurate Maury potential and so on, but also highlights one important and I think interesting piece of physics here. The piece of physics that is that you have a Maury system with a lattice parameter of about 6 nanometers. And the exciton, even for this relatively small Maury lattice parameter, is localized in this region of about 1 nanometer, and the diameter is about 3 nanometers or so. And that means that you really have a localized bosonic-like excitation, this lattice of exons. And this really says that this particular kind of exons are indeed potentially a good way to realize this kind of solid state analog to atomic physics of bosonic traps into a lattice. So we're quite, of course, excited about this direction and more broadly how we can think about localization and engineering of excitations in Maury systems. But I'd like to switch gears a little bit and tell a little bit of also a work that we are just finalizing that we also think is exciting in the direction of how we can understand the lifetimes of these excitations. And it is the following. I mentioned my beginning of my talk that if you look at this optical absorption spectrum, you can actually include those final lifetime effects. And with that, it can actually explain the experimental spectrum in a quite adequate way. This, it turns out, is relatively well for higher temperatures, but this kind of formula actually breaks down for lower temperatures. And I'll tell you why that's the case. So these sort of ideas were based on earlier attempts to include exton-phonon interactions. They're actually approximate. And the way that those earlier formalism worked out is that one would express the lifetime, or basically the exton-phonon kind of interaction, as a linear combination of the electron lifetime and the whole lifetime due to electron-phonon interactions, and weight those lifetimes by the exton expansion coefficient that I introduced to you last time. But it turns out that the actual expression that was more rigorously derived recently is more complicated. And the reason is that in an expression like this, you're actually mixing the final state. The initial state is an exton, the final state is a free electron. But in reality, the lifetime of one exon due to phonon interaction is that you start with a coherent extonic state, you scatter with a phonon, and your final state is still a exton. So in reality, what I have to do is work with basically Fermi's golden rule kind of picture that look like this. You basically start with an exon S, the final state is another state S prime, and you either emit or absorb a phonon, and there's either a electron channel or a hole channel that is schematically shown here, and you conserve energy. So what I want to mention is that basically, perhaps a simple physical picture is that if you ask yourself, what is the lifetime of a neutron? Lifetime of a neutron in vacuum is 15 minutes, but atoms are stable in our body. So it means that really we cannot try to understand the lifetime of one exton as a linear combination of the lifetimes of the particle that make that exton. That's particularly important is if you're looking at low energy states in your system. This expression here, you can also cast that into self-energy form and so on, but it basically involves you computing the electron-phonon vertex. So basically the coupling of this phonon between two extonic states. This is basically a rotation of the electron-phonon interaction to the sort of exon basis, and it can be described like this. If you denote by G, lowercase g, the electron-phonon vertex, either between electron states or hole states, you can contract these by the exton expansion coefficient A. And this is the way that you actually deduce this exton-phonon vertex that is shown schematically here, that actually couples one initial exton with principal quantum number S a wave vector q to final state S prime at q plus lowercase q. Okay, so how do we implement this in practice? So I'm showing some results that we have for monolayer molybdenum sulfide. The lower energy states and lower energy exton is that q equals to is actually q equals to k. And let me show you what I mean by that. The quasi-particle band structure is shown here. The direct band gap is direct from k to k. So there is one exton that looks like this with zero momentum. There is one exon with final momentum of k like this. And there is one exon with momentum q that involves electron here at the k prime point and the electrons at the m point. So if you solve the beta salpeter equation for all possible states, you get this band structure for the extons shown on the panel here. I want to highlight that the lowest energy states, either at k or at gamma, basically this or this, the lowest energy state actually is a spin forbidden exciton because of the basically spin orbit splitting of the valence and conduction bands. The exon that you see in an experiment is a little bit higher in energy. It's 1.78, it's right here. And already here, there is something that is quite interesting that you can obtain already from our calculation, which is that the relaxation time is actually longer for the higher or the second state relative to the lowest state at the gamma point. The reason actually is related to the spin physics. Basically, the lowest energy state, even at 300 Kelvin, it can actually scatter up to this M point, which actually has the same spin physics. But the higher energy dipole or spin allowed state can no longer scatter to the M point. It can only scatter to the outer valley, but that process is not really likely. So in essence, you can compute all this kind of Brillouin zone resolved matrix elements, scattering time, and so on. So the question is how, in the last few minutes, how do we now collect all those elements and address the question of what is the coherence time and what is the line width of those excitations, even at low temperature. And it turns out that we realized that the way that people typically think about this is not quite correct, in the sense that you might think that if you take the basically the exton phonon matrix vertexes GSS, those diagonal entries, and square them, those should be related to the lifetime. And it turns out that that is actually not correct. The reason is that this is a kind of a multi-band physics. It was actually emphasized in the past by Toyozawa. It was actually done in the context of a semiconductor block equation by Andrea Knorr and collaborators. But I think the fundamental physics is that light absorption is actually not a first order process. It is rigorously a second order process. And this was highlighted by Hopfield in the 1958. So what does that mean? If you, one way to rephrase this in a kind of more modern framework is the following. The way that you may think that one has to address light absorption, including lifetime effects, is that one should sum over all final states, and those parabolas here show the different exton bands. You go to the ground state to the different exton state. Those are the S states, and each band may have a finite lifetime. So you would naively substitute the energy conserving delta function from his Gonda rule by basically a Lorentzian-like distribution. But what Hopfield actually showed, and what we're putting in the first principle formalism, is that this process is really second order, in the sense that you actually shine light, you go to an intermediate state with a band number S prime, and via interaction with phonons, you scatter to another exton band with another momentum Q, and that's actually your final state. It turns out that this kind of the second order process contains the same number of phonal vertices and electron photon vertices. So it actually, in terms of perturbation theory, they are the same order. But here is this is really a second order process that is approximated to look like a first order process. But it turns out that this is incorrect. And what you're missing is that those off diagonal coupling between S prime being different than S. So if you work that out, what happens? So I'm showing the main result shown in the bottom right corner. Basically, we can now predict the absorption spectrum as a function of energy for various temperatures. As you expect the peaks become more broadened, you have basically both the A and the B extonic peaks. And very interestingly, we can compute what is the change of the line width relative to, say, zero temperature. If you actually include this diagonal approximation that people typically use, it turns out that you dramatically underestimate the line width by a factor of 3 or so.
And those off-diagonal effects that I mentioned are quite important if you want to describe, experiment. And really those off-diagonal are really important in those systems because this multiband physics is exacerbated by the fact that you have very strong excitonic effects, and you can have intermediate states from a higher Rydberg state 2s and so on that give rise to this intermediate state contribution. We're also looking forward to looking at more complicated systems. We have preliminary data working on precisely those bilayer that we mentioned and understanding the ultra-fast charge transfer process. We can now actually compute the exon phonon coupling throughout the Brillouin zone for all those systems, but it's quite computationally demanding because your exon lies in the continuum of transitions, which means that I have to include basically a very fine K-point sampling, a very large number of exons with different final momentum, and a very large number of exon bands. So right now, the challenge that we have to deal with now hundreds of terabytes of data to process, but I think it'll be very interesting to see whether there are stochastic and other algorithms to make those approaches more numerically efficient in the future as well. So I hope that it convinced you that there's quite interesting physics associated with those Moiré exons and also this interaction with phonons that we can also compute from first principles. And with that said, I also want to mention that because my group is pretty new, we are also interested in other properties associated with basically large-scale systems. We're also interested in multi-particle excitations from first principles and also nonlinear and nonlinear equilibrium phenomena. In particular, we have a way that we can basically solve the GW kind of the equation of motion from the Green's function within the GW approximation from first principles in the time domain. And that allows you to understand, for instance, the shift current that our speaker mentioned this morning in a more systematic way without a real expansion by simply looking at the response function in real time and Fourier transforming that. So with that said, I'd like to acknowledge my group members. The first part of the talk that Thieu is done by student Jonathan Georgaras, who joined during the peak of the pandemic. And I also like to acknowledge all the other collaborators, especially in the part involving exon phonons. The bulk of the work was done by Yang-Hao Chen, now at Academia Sinica, also Diana Chu, Mit Naik, and Jonah Haber at Berkeley, and our experimental collaborators, the Okinawa Institute of Science Technology, Keshav Dani, and Tony Hines for the spectroscopic. So with that, I'd like to thank you all for your attention and sticking to the end of my talk.
Thank you very much. Is there questions?
Hi, Felipe. Nice talk. Yeah, regarding the first part, when you were showing the Moiré exciton, we're estimating the radius. The calculation seemed to have been done on like an ideal bilayer, or maybe what you have been showing. So yeah, I just want to know whether you expect that the radius would get actually even smaller. So in that case, actually even a better agreement with the experiment, because I think you're
yeah, that's an excellent question. And in fact, that could be the case. We have a new so we actually, I think that we partially solved this with two different ways that I didn't mention here. We have one way that is actually led by Mit Naik, now at Stephen Lewis group, that we basically do a brute force beta salpeter equation calculation on this large system. Mm-hmm. And this is still ab initio, but the idea is that you use a basis set that converts your calculation faster. You basically take your Moiré unit cell and write those states in terms of monolayer states. And one way that it can actually obtain on the same footing the electron hole correlation. We're also looking at another way to do this, basically by generalizing all those ideas of Moiré potentials. Basically, we're generalizing the beta salpeter equation to treat on the same footing the electron hole interaction and also the interaction with the Moiré potential. Some correction that is quite important for the radius. But the main challenge with that we're solving right now is how we actually determine the Moiré potential individually for the electron hole for those systems. So that's something we're actively working on.
I see. Okay, thanks.